pretending.
Mercury.
Are they
In case Mercury surfaces in concrete. The second most important geologic process to affect Mercury is volcanism.
I believe I'm keeping you from your person. I will be here this evening to share your great triumph. My apologies. Thank you, Mr. Nicole.
Chuck, Queen tonight get tonight. We must not at home tonight.
The Queen hails from extinct cinder cone volcanoes, and geologists suspect similar parts can be found on Mercury.
This is a cinder cone. You can see behind me there's
And
one
a child.
crater in the center, which is those cinder cones.
These volcanoes do have their differences, but the cinder cones
Because Mercury has less gravity, we would expect them to be cinder cones that form wider and much flatter.
all volcanoes erupt when the pressure from the magma or molten rock inside is greater than the strength of the rock beneath. Pressure increases for two reasons: too much magma and too much gas. And when pressure increases in a volcano, it usually has one place to go.
Lava comes off the surface and erupts explosively. You have a vent area, and you have what's called fire fountains.
If the pressure is great enough, its force can spew lava higher than 100 feet on Earth. But on Mercury, with such low gravity, the fountain could eject lava 30 stories high. While these cinder cones may result in demonstrating a shock volcanic areas of Mercury, witnessing eruption there firsthand and watching cinder cones form is a whole other experience. Without these figures, school actions available across the world.
All the marvelous art
That material would go into essentially back into space because Mercury doesn't have an atmosphere. So that material
Yes,
would break
I
up
did.
much more.
Also on Mercury, you will be able to hear the
Since Mercury has no gravity,
playing a guitar or a ukulele or a piano, you would not hear it because there's no atmosphere to transmit that sound. So it would be just complete silence.
Back in 1974, Mariner 10 surveyed only 45% of Mercury's surface on a flyby mission. 30 years later, NASA launched the Messenger spacecraft. The satellite will map the entire planet and transmit data to eager scientists with a deluge of unanswered questions.
I want to see the other side. I don't know what's over there. That's been bugging me for 35 years. Is it like the side we saw? Or is there something very unusual and different?
But even with resources being earmarked for future exploration of this rumpled dwarf in the solar system, exactly how different or similar we really are may be left up in the air. Despite the harsh conditions on Mercury and on Venus, a close look around our own backyards reveals the good, the bad, and the ugly of the inner planets.
The universe is this vast, vast thing, and here we are sitting on this little pinprick, but we are not isolated.
We see things that happen on these other planets, tremendous climatic changes. In the past, it happened in a very short period of time to change that. And that can happen on the Earth.
Ultimately, it's just our knowledge of who we are, how unique and how rare an environment like ours and even creatures like us might be in the universe. And that evolution, that exploration, that turning the corner, that discovery of new ideas is what we're all about. There's a bright future.
Both having the joy of movement. In the beginning, there was darkness, and then, giving birth to an endless expanding existence of time, space, and matter. Now see further than we ever imagined, beyond the limits of our existence, in a place we call the universe. Are we alone in the universe? Are we the only ones who look up at the stars and wonder, is anybody out there? Today, scientists quest for the answer in different ways. Some with massive radio telescopes, some with interplanetary and interstellar probes. If we find extraterrestrial life, what will it look like? Soft and squishy? Or will the first aliens we contact simply be self-replicating machines, their biological creators having died off millions of years ago? Some of the top scientists in the world probe for answers in the search for ET. It is the question that has kept many people awake at night, staring at the stars, pondering the possibilities. In a galaxy filled with 1 billion stars, in a universe filled with 100 billion galaxies, are we alone? The incredible vastness of the universe is difficult to comprehend, but here's a way to consider it. If you were to shrink the sun down to the size of a marble, put it on a sidewalk in downtown Manhattan, the Earth would be a pinprick about 4 feet away. Mars would be 2 feet beyond that. The nearest other star where we might hope to find intelligent life, Alpha Centauri, would not be 10 or 100 feet away. It would be in Washington, D.C., 230 miles distant. And another star might be as much as 7,000 miles away, in Rio de Janeiro. But if we ever did chance upon voyagers from these distant points of the cosmos, what would they look like? Would they be basically the same as us? Would they be fundamentally different? Could they be perhaps so strange and unusual that they are unlike anything we ever dreamed or dreamt could exist? Many believe the quest for extraterrestrial life must only begin with intense scrutiny of how terrestrial life on Earth, might have begun. And in the early 1950s, 2 chemists at the University of Chicago advanced understanding of life's basic chemistry dramatically. Nobel laureate chemist Harold Urey and graduate student Stanley L. Miller concocted a batch of primordial soup. They injected methane, ammonia, hydrogen, and water into a closed system of glass bulbs and tubes. These chemicals are thought to have been commonplace on early Earth.
If you put all of these things into a container and you supply some form of energy to do some kind of reaction. What do they make? What kind of reactions go on?
Miller and Urey energized the mix with electrical sparks to simulate life. The results were, well, electrifying.
They got a brown sludge on the wall of their chamber. And when they started analyzing that brown sludge, there were lots of organic materials in it, and some of them were amino acids. Some of the precursors, the building blocks for proteins.
Proteins, of course, are, in turn, the building blocks for life. The Miller-Urey experiment had demonstrated that the precursors of living organisms could have gotten their start from a chemical reaction. And such reactions aren't limited to Earth. Methane, ammonia, hydrogen, and water are plentiful on other cosmic bodies within our own solar system, and many scientists believe throughout the universe. Indeed, noted astronomer Carl Sagan, speaking of the Miller-Urey test, stated that no other single experiment had done more to convince scientists that life is likely abundant in the cosmos. But the presence of water was key. Such a chemical reaction could not have taken place without it.
Water is very good at dissolving materials, much better than any other liquid. So you can dissolve all sorts of nutrients, chemicals, products, things like that, or catalysts, things that go through the chemical reaction with water. So water is an excellent liquid for storing all those.
On Earth, where liquid water exists, no matter how extremely refined, some form of life also resides. It resides at ocean depths so great sunlight cannot reach them. It resides in damp rocky crevices miles beneath the Earth's surface. And it even resides in the extreme salinity of an ancient California lake, with a salt content above 10%. That's 3 times the percent of salt in the ocean. But life on Earth also has carbon, which was in fact the primary substance generated by the Miller-Urey experiment. All life forms, as we know them, consist in large part of carbon molecules.
Life needs some sort of ability to create long molecules to store information. So carbon is amazing at building long molecules. So for example, the DNA molecule is sort of 1 billion base pairs long. If you stretched out a single DNA molecule from one of your cells, it would be a yard long from a single one of your trillions of cells. And so you need something that can store absolutely a huge amount of information that it takes to build a creature like a lion or a human or a tree.
But if life has taken hold elsewhere in our galaxy or beyond, would these conditions necessarily hold true? Would extraterrestrial life be water and carbon based? Would DNA shape intelligent life? And would the aliens look anything like us?
Maybe they would look a little bit like us, but that would be very, very coincidental. I mean, I just saw, Grant squirrel running behind a bush over here, and he inhabits the same planet I do. He's got DNA, probably 70% of his DNA is the same as mine. He doesn't look like me, so why would the aliens look like me? They probably wouldn't.
A scientist who has spent time pondering such questions and rendering speculative alien forms is Dr. Robert Hurt of the California Institute of Technology. Hurt is a visualization scientist who uses data returned by the Spitzer Space Telescope to render images of deep space objects and processes.
To try to find the best visual ways of explaining complex technical concepts, but through imagery. Planets that are being studied around other stars, the ways that stars and nebula form, processes going on in galaxies, the distant universe, all the way out to the Big Bang.
But for this program, Dr. Hurt has agreed to use known scientific data to render a speculative alien life form. For his alien world, he's chosen Jupiter. A real challenge, since Jupiter is essentially a giant gas ball.
Here we have a place where there is no land to speak of. The atmosphere is made primarily of hydrogen and helium gas, though it's rich with organic compounds. And as you go deeper into the atmosphere, it gets warmer at much higher pressures. So, as a kind of thought experiment almost, it was posed, what could you imagine living in an environment like that?
Referencing the only known model for life, living organisms on Earth, Hurt began by asking, what does life on Earth need?
You need sources of energy. You need the chemicals that life on Earth needs to build, the materials that it's constructed from.
On Jupiter, a primary source of energy is faint radiation from the sun, striking the top of the planet's atmosphere. And the only known source of chemicals for use as building blocks for life are the organic compounds swirling in the Jovian cloud blanket. In considering a potential life form that could take advantage of both long term, Dr. Hurt remembered an idea originally postulated by Carl Sagan in the 1970s. The notion of a sort of living gas balloon. Such a creature could remain aloft in Jupiter's atmosphere indefinitely.
Now, of course, there's a problem with Jupiter, that Jupiter's atmosphere is already made of the lightest gas we know of, hydrogen. So you can't really make a lighter than hydrogen balloon. But if you want a balloon to be able to float in Jupiter's atmosphere, it actually has to be a hot air balloon.
Hurt has invented an extraterrestrial organism that is really more plant than animal. A balloon-like plant inflated and kept buoyant by hot air.
Now, it's going to be really expensive in terms of biology to generate that heat yourself. So instead, if we imagine a creature that has a very dark skin, very thin, that allows solar radiation to heat the gases inside, you might be able to create something that will levitate, at least during the daylight hours, just by absorbing solar radiation.
At night, the plant would lose its heat source, but Dr. Hurt has allowed for this problem in the creature's design.
It also has a shape that is well adapted to act kind of like a parachute that can ride thermals when it's not able to heat its own gases and float like a balloon. So in the nighttime, it might sink down lower into the atmosphere, but by finding thermals, it can ride this up like a glider almost.
Time spent at lower altitudes would actually be beneficial to the creature. It's here that its food is most plentiful.
I've given it a kind of an air root system that hangs at the bottom. When it sinks into the lower parts of the atmosphere, it can screen out and pull up some of those organic compounds we know exist in the atmosphere of Jupiter.
Of course, Dr. Hurt's creation of the Jovian balloon plant represents nothing more than an entertaining exercise in extreme, though science-based, speculation. But the possibility that some form of life might actually now exist on other cosmic bodies in our solar system is very real to many astrobiologists and geologists. And one such body is right next door to Jupiter, the ice-covered Jovian moon, Europa.
Oh, what a good time we will have. You should make it happen. Yeah.
Go Tally, the joy of movement.
After 18 years, I'm finally free.
They're just out of prison.
What's your worst feeling? I'm about to take an inmate in to live with me.
Some people will do anything to keep their freedom.
We have a list of rules.
The hell did I get myself into here?
Your life is on the line.
I got a lot to do. It's very important for me not to go back to prison.
How far would you go?
We're done here from leaving.
Inmate to roommate. Stream the new season now. This winter, meet the heroes of performance. Only available at the Acura Season of Performance. This winter, visit your local Acura dealer for attractive offers on the MDX.
Well, here's to first dates. You look amazing.
And you look amazingly comfortable. When your V-neck looks more like a U-neck, that's when you know it's half washed. Try Downy fabric conditioner. Unlike detergent alone, Downy has 7 benefits that condition and smooth fibers, so clothes look newer, longer. Feel the difference with Downy.
$370 million miles from Earth, orbiting the giant gas planet Jupiter, is the most likely harbor for extraterrestrial life in our solar system, Europa. It's an ice-covered ball about the size of our moon, about 1/4 the size of Earth. Scientists believe the ice on Europa is covering a global ocean of liquid water. A convincing indicator is that Europa is a conductor of electromagnetic energy. It conducts the magnetic field generated by Jupiter.
This conduction is the signature, or we think it's the signature, of salty water inside Europa.
It's believed that the water layer on Europa might be as much as 100 miles thick.
Now remember, Europa is similar in size to the Earth's moon, so that means that even though it's a smaller body, it actually has twice the amount of liquid water of all of the oceans on Earth put together.
And of course, liquid water is what makes life possible on Earth. So scientists who make it their business to quest for extraterrestrial life are keenly focused on the study of Europa. But how could liquid water, which freezes at temperatures below 32 degrees Fahrenheit, exist on a moon 5 times as far away from the sun as the Earth? Europa orbits Jupiter in an elliptical pattern. Sometimes it's close to Jupiter, and sometimes it's farther away.
When it's close to Jupiter, it gets stretched by Jupiter's gravity, but it's an effect that we call tides. When it gets further away, it's stretched less. So it means that the body of Europa is continually worked.
Friction caused by this stretching generates heat, just as a rubber ball heats up when it's squeezed repeatedly. At the planetary scale, this process is called tidal heating, and it creates enough heat, possibly, to keep H2O miles below the surface of Europa in liquid form. It also appears that this stretching causes fractures in the Jovian moon's icy crust.
Imagine if you're trying to change the shape of an egg. What would happen to the shell? The shell would crack. And so when we look at the surface of Europa, we see lines all over the place, which are almost certainly marking the locations of cracks.
The cracks appear to open and close frequently, and the potential for these cracks to allow subsurface water to interact with the surface has important implications for the possibility of life on Europa.
Water from the ocean is going to rush up into the crack. When it rushes up, it's going to freeze. Start to freeze. A few hours later, when the crack closes, it's going to squeeze and slush off to the surface. And so wherever we see these lines on Europa, there are double ridges, one ridge lining along each side of the crack.
Most of the water come down and sloshes back down into the crack to the ocean below. It's likely to carry with it some of the building blocks for life that have seeped down to the surface. The top of Europa's ice layer holds oxygen. It's been separated from the H2O in the ice by charged particles in Jupiter's magnetic field.
In addition, the surface of Europa likely has organic compounds that come down from comets and bits of comets. So again, the surface has another ingredient that's important for life.
Dr. Richard Greenberg of the University of Arizona has graphically depicted how potential life forms might take advantage of the ecosystem created by a crack in Europa's icy crust.
Although the outer few inches would not be a good place for life to live because of radiation, once you go down just a few feet, life would be safe from radiation and also get enough sunlight for photosynthesis. So you could have an organism at that level that photosynthesizes, and it would be connected to the ocean by this tidal water that rushes up and down every day.
A day on Europa is much longer than a day on Earth, about 3.5 times the length of an Earth day. Time for mobile organisms to venture into the fissure.
You can imagine other organisms that grasp onto the walls of these cracks and just exploit the flow of ocean water coming past them every day.
Even mollusk-like or jellyfish-like creatures might rise with the water into the cracks to take in fresh nutrients from the surface. Life in Europa's ice-covered oceans may also draw energy and nutrients from a place other than the icy surface. It's possible that residual heat at Europa's core has resulted in deep-sea hydrothermal vents. On Earth, such vents host multiple forms of exotic life.
What happens is that reducing water that's very hot and has lots of heavy metals comes out through the groundwater and is ejected into the ocean itself. There's a huge gradient in the chemical composition that life can feed off of. This chemical source of energy allows huge populations of bacteria and other very small life forms to exist. There's a whole ecosystem, a whole food chain on top of that, leading up to fish and various worms that thrive at those locations.
In recent years, talk has arisen of sending a lander to Europa that could penetrate the ice and probe for life. But Europa expert Richard Greenberg believes that a lander might uncover signs of life without penetrating the ice.
If we send a spacecraft to Europa to look for life, it might be pretty easy to find it, easier than people have realized. Most planning has considered how do we get through these miles of ice to get down to the ocean? How do you drill through or melt your way through? It may not be necessary. If you can land in a place where liquid or ice has come up from the ocean recently, you might find signs of organisms in that ice. Or if you land really smart and find an active place, you might actually be able to sample real fresh oceanic water.
The risk in that case, some feel, would be contaminating the icy movement.
So if we had microorganisms that stowed away on a spacecraft and landed on the surface of Europa, and those microorganisms found their way into the liquid water of Europa, we might later discover life on Europa that was life that we had sent there.
But elsewhere in our solar system, on another distant moon, earthly contamination isn't a danger. Life here would simply be too exotic.
With the Salvation Army, your love lasts all year long. It puts a present under someone's tree today and a roof over someone's head tomorrow. Together, we love beyond Christmas.
Did you know some of your detergent's fragrance disappears in the dryer? Downy in-wash scent boosters survive the washer and dryer for freshness that lasts.